In this video, I want to talk about D-Latch. So if you remember from the previous video, when I talked about the SR latch, I said that there are two main problems with the SR latch. One is we have this invalid case in which when S and R are both ones, both Q and Q bar become 0, which makes Q to not be the complement of Q bar. The other issue that I talked about for SR latch was that in order to set or reset the output Q, we need to have two inputs, one S and one R. So even though we are working with logic circuits and the only possible values are 0 or 1, in the SR latch we needed to have two variables or two inputs to be able to set or reset one output. So in the D-Latch, these two flaws are solved. More specifically, something that was not that obvious with the SR latch, but when you talk about the concept of sequential circuits, there is an element of time involved as well. So with the SR latch, there was no element of time. We had a set input and a reset input. There was no time input. So for the D-Latch, what we have is we want to avoid all the problems of the SR latch. So a D-Latch in general has two inputs. One is the clock signal and the other one is the D or the data input. So symbolically, the D-Latch is shown like this. With the rectangle, clock is entering the D-Latch from top part or the bottom. The input is from the left side, D, and the outputs Q and Q bar on the right side. So for the SR latch, we had both set and reset to either make Q to be 0 or 1, right? We didn't have control over time. Or in another word, the time and the value that needed to be stored on the latch, these two concepts were kind of combined. So we want to have this separation as well. So because of that, we say we have a clock signal that controls when the output changes or when the storing happens. And we have a D or the data input which controls what the output changes to or what is being stored in the D-Latch. So now that we have these basic definitions or basic requirements for the D-Latch, let's just go over the functionality of the D-Latch. So the D-Latch, when the clock is 1, D passes through to Q. So that means that when clock is 1, whatever value you have in D will be seen in Q. So that is equivalent to saying D-Latch is transparent to the changes of D. So when clock is 1, if D is 0, Q becomes 0. If D is 1, Q becomes 1. So whatever change we see in D, we will see the exact same change in Q. On the other hand, when clock is 0, Q holds its previous value. So in another word, when clock is 0, no matter what you change D from 0 to 1 or from 1 to 0, it doesn't matter. Whatever was the value for Q before clock becomes 0, it stays at that. So that is the memory functionality of the D-Latch. In addition to these functions, we want to avoid invalid cases as well. So how can we combine all these requirements into a simple design? The answer to that is very simple. So the internal circuit for a D-latch looks something like this. We have an SR latch that is connected to this additional combinational circuit. So this is an additional combinational logic circuit. So we have clock, we have D as the two inputs to the circuit, and then we have Q and Q bar as the output. So let's just go over the possible combinations for the two inputs. So for this circuit, we have 4 possible combinations for the inputs. We have 0, 0, we have 0, 1, and I will tell you why I use X. And then we have 1, 0, and then finally 1, 1 for clock and D. So let's just go through them one by one and see what we have. So when clock is 0, that means that the input to this AND gate is 0, which makes its output to be 0, right? So it doesn't depend on the value for D bar, basically D that goes through this inverter. So when clock is 0, the value for R is 0. On the other hand, when clock is 0, this input for the second AND gate is 0, which makes S to be 0. So again, when clock is 0, no matter what is the value for D, the output of these two AND gates is 0. So these two outputs from this combinational logic circuit that we had on the left are fed into the SR latch as R and S inputs. So we have S to be 0, R to be 0, and then for this one D bar is 1, for the second one D bar is 0. So the reason that I put X or don't care here, because the value for D does not matter when clock is 0. So the same is true for the value for D bar as well. So now in the SR latch, we know that when the two inputs are 0, the outputs are the previous values of the outputs. So the value for Q is going to be the previous Q. And the value for Q bar is going to be the previous Q bar. So this is the memory functionality. So this basically is the result of analyzing 2 cases of the 4 possible combinations. Clock 0, data 0, clock 0, data 1. So when this happens, the output is going to be the previous Q. Or in another word, when clock is 0, the output remains at its previous value. Now let's see what happens when clock is 1. So when clock is 1, and here also when it's 1, and then when D is 0, that makes D bar to be 1. So here we have 0, here we have 1. Now for the first AND gate, that is the result of ANDing clock and D bar. Both of the inputs are 1, which makes R to be 1. So R is 1. For the second AND gate, we have the result of ANDing 1 and 0, which makes R to be 0. So that means that the inputs to this SR latch are going to be R equals 1 and S equals 0. Do you remember what was the output for an SR latch with this input? Q is 0 and Q bar is 1. So that is equivalent to resetting the SR latch. So as you can see here, when clock is 1, D is 0, the output for Q becomes 0, for Q bar becomes 1. Let's just go for the final combination for when clock and D are both 1s. So when clock is 1 and D is also 1, that makes D bar to be 0, and here D is 1. So for R, we have the result of ANDing clock and D bar, or 1 and 0, which makes R to be 0. For S, we have the result of ANDing 1 and 1, which is 1. And then D bar is 0 because D is 1. So now, in the SR latch that is connected to this combinational logic circuit, we have R being 0, S being 1. That is basically setting the SR latch. So it makes Q to be 1 and Q bar to be 0. So that is setting the SR latch. So now if you look closely, you see that the value for Q for when clock is 1 is exactly the same as the value for D, or the data. So that means that in the design of the D-Latch, whenever clock is 1, whatever value we have for D is going to be seen in Q. And that is what we called as being transparent, right? We said that when clock is 1, the D-Latch is transparent to the changes in data. So that is basically the transparency. On the other hand, when clock was 0, Q was its previous value. So that is the definition of the opaqueness. When clock is 0, the D-Latch is opaque to the changes of D. So it means that whatever change you have in D, it is not going to be reflected in Q. One other thing that you might notice here is that we don't have this invalid situation anymore, because there are no cases for which both S and R are becoming 1. So either R is 1, S is 0, or S is 1, R is 0. So the design of D-Latch helps us to avoid the problems that we had for the SR latch. But the D-Latch is not perfect by itself. And the issue arises for when we have clock to be 1. So when we have clock to be 1, as long as clock is 1, whatever change we make is going to be reflected in the output. So let's say we have a clock signal that is basically looking like this. It switches back and forth between 0 and 1. And the reason that I show it with these slanted lines here in the points of transition is that, ideally speaking, we don't have a perfect sudden jump from 0 to 1 or from 1 to 0. So that's why I draw it like this. So in the design of the D-Latch, whenever we are in this region, for which clock is 1, whatever change that we have in D is reflected at the output. So assuming that we have a clock signal that looks like this, which 50% of the time is 1, 50% of the time is 0, that means that half the time whatever change we make in the value for D is going to be reflected at the output. So that doesn't give us that much synchronous behavior, right? Because synchronous behavior is when you have changes only being recorded at specific times. So it is more preferable, so you have only changes that are recorded in very short periods of time. So what if we have change to only be stored in the rising edge of the clock or in the falling edge of the clock? So that is more preferable in practice. In the next video, I will go over the design of the D flip-flop